Hi everyone, and today I am going to discuss an interesting and an important topic in computer science, that is scalability and data driven parallelism, especially focused on sparse matrices. This is the agenda for today's session. At starting, we will discuss what are sparse matrices and how we can store these sparse matrices. And slowly we will move to the concept of scalability and data-driven parallelism, and we will see some techniques for parallel processing in sparse matrices. And at last, we will see the real-life applications of these sparse matrices. In general, a matrix is a two-dimensional object made of rows and columns. For example, let us consider there are m rows and n columns. So the matrix have a total of m cross n values. If the most of the elements of the matrix have zero value, then the matrix is called as a sparse matrix. In general, a sparse matrix is also a matrix. It has all the properties of the matrix and we can perform all the operations. But the main difference is the number of non-zero elements are less than the number of zero elements. So here you can see an example of a sparse matrix. If we consider the first matrix, the number of non-zero elements are less than the number of zero elements. But in the case of second matrix, it does not have any zero elements. So basically we can say that it does not have zero elements. So the number of zero elements are less than the number of non-zero elements. So it is not a sparse matrix. But here comes a question, why do we use sparse matrix instead of original matrix? We have two use cases. First one is storage. There are lesser non-zero elements than 0 and thus lesser memory can be used to store these elements. And the second one is computing time. Computing time can be saved by logically designing a data structure traversing only non-zero elements. Now we will see the representation of the sparse matrices. We will store the non-zero elements instead of the zero elements to reduce the memory space. There are commonly two ways of representing a sparse matrix. First one is coordinate list or the three-column representation. In the coordinate list, we will store the data in a 2D array which has three columns, row, column and the element. The first row represents the dimensions of the matrix and the number of non-zero elements present in the matrix. From the second row, we will store the data of the non-zero elements. The first entry represents the row number of the element and the second entry represents the column number of the element and the third column represents the element present at that particular position. In this way, we will store the entire matrix in the form of a 2D array. And the second way to represent a sparse matrix is the compressed sparse row. This is a more efficient way to store and manipulate sparse matrices. It compresses the row information and stores only the non-zero elements, which makes it particularly useful for matrix vector multiplication. CSR uses three one-dimensional arrays values. This array stores all the non-zero elements of the matrix in the row-wise manner. And the second one is the column indices. This array stores the column indices corresponding to each non-zero element in the values array. And the third one, the most important one, is the row pointer array. This array stores the starting index in the values array for each row of the matrix. Now let us take an example and analyze how these are stored. In the given example, the non-zero elements are listed in row order in the values array, that is 3, 5, 7 and 9. And the column indices of the values are 2, 1, 0, 3, which are the corresponding column values of the non-zero elements. And the third, the important one, row pointers. Here 0 means the first row starts at the 0 index in the values array, and 1 means the second row starts at index 1, and 2 means the third row starts at index 2. 4 is the end marker indicating that the third row ends at index 4 in the values array. In simple terms, we are storing the cumulative values of the elements in the row pointer array. And the mainly use cases of CSR is memory efficient and fast access, which makes it useful for performing faster operations on the matrices. To understand the concept of scalability, let us take a real life example. We all know that recently India won the T20 World Cup. In general, in olden days, we will watch the match in TVs. But in this new generation, this is also streamed online in the internet. This match is streamed in Disney Plus Hotstar. Since it is a final match, more than 6 crore viewers have logged in and seen the match. Have you ever wondered how Hotstar manages these many accounts and keeps track of all these accounts? This is what scalability is. It refers to a system's ability to handle increased load without degrading any performance. There are mainly two types of scalability. First one is horizontal scaling. This is also called as scaling out, adding more machines or servers to handle the load. And the second one is vertical scaling. This is also called as scaling up, adding more power to your existing system to handle heavy load. So by doing this, you will able to distribute the workload across multiple systems, enabling your company or website to handle more customers and serve a large customer base. Now we will see how this concept of scalability is useful in sparse matrices. In sparse matrices, the scalability it refers to the ability of the algorithms and the data structures and the resources which are used to handle these large matrices. These all work should be done without increasing the time complexity and the space complexity as linear or exponential. We are achieving scalability by storing only the non-zero elements, which means that we are reducing the memory space and we can handle much larger matrices in a similar way with less memory storage. As we have seen before, if more users are entering, we need to upgrade our website, otherwise it results to crashing. In the same way, as the matrix size grows, the scalable sparse matrix avoids unnecessary computation and stores only the non-zero elements and focus the operations only on the non-zero elements. So this ensures that performance remains same even when the data is increased or scaled up. So in a scalable sparse matrix, the computations often involve parallel processing, which means that each task is divided into subtasks and given to multiple processors. This is beneficial for when we are dealing with large sparse matrices, as it allows the workload to scale across many nodes, which increases the performance and decreases the cost. And the scalable algorithms for sparse matrices are designed in such a way that they skip zeros and making them faster and more efficient for large scale matrices, since we are avoiding most of the elements which are zeros. Here is a sample figure of the two types of scalability. In this picture, you can see the example of the horizontal and vertical scaling. In horizontal scaling, the number of units are increased. In the vertical scaling, the power of a single unit is increased. Now let us see the concept of data-driven parallelism. To understand this, we will take a real-life example. Imagine a toy factory which manufactures toys. If all the works like manufacturing, storing and selling, all these works are done by a single person, then it will be a nightmare for him. So data parallelism is a technique in which we will divide the large task into small subtasks and we will assign each task to a processor or a worker. So these processors perform the same operation on multiple pieces of the data at the same time. So the goal of the data driven parallelism is to improve the computational speed. How this data driven parallelism works? This works on simply four terms: divide, distribute, conquer and combine. Divide. The task, the bigger task is divided into smaller subtasks. Distribute. These subtasks will be distributed among all the processors or workers available. Conquer. Each worker will perform their task individually at the same time. And at last, combine. We will combine all the individual tasks done by all the processors to get the final output. And some key concepts in data-driven parallelism are data partitioning. We need to divide the data in such a way that there should not be any common work done by any two workers, and these tasks should be independent, which means that one task should not affect the another task. Task scheduling. We need to schedule these tasks to all the workers available in a organizable way. Load balancing. We need to make sure that each worker gets the same load. We need to avoid overload of data for any worker if it occurs. These are some information and some things which we need to take care when using data driven parallelism. The first one is synchronization. There should be some synchronization between the processor such that there is no data loss in the entire work. In simple terms, all processors should work together at the same time. And the second one is communication overhead. This represents the cost of coordinating between processes. In operating system, this is also known as inter-process communication. And third one is the scalability limits. If we add more processors to increase the speed, it results in degrading the performance due to the increased complexity and overhead. And the last one is fault tolerance. We need to ensure that this all happens without any failures. Otherwise there is no use of using this technique if there is an error. So we need to avoid all other errors, and if one processor fails, the entire system should not crash, and the failed task should be done by the other processor to fix the errors. And the benefits of data driven parallelism is improved performance. The performance will be improved as one processor does not do all the work. And scalability, as we have seen the concept of scalability before, data driven parallelism ensures scalability in a high factor, and the resources will be efficiently utilized since all the components or all the processors are used at the same time. And the throughput is also increased because of high amount of tasks are completing in a short amount of time. Now we will see how this data driven parallelism is used in real world scenarios. In machine learning, training large models on massive data sets involves performing similar computations on different subsets of the data. Data driven parallelism is commonly used in distributed training frameworks where each processing unit works on the portion of the dataset simultaneously, that means at the same time, which increases the speed of the training process. In image and video processing, an image recognition or rendering and video require application of filters and transformation. We need to analyze each individual frame or segments. Data driven parallelism allows us these tasks to be parallelized. That means we can divide the work with each processing unit handling a subset of images or frames concurrently. In computer graphics, rendering a high resolution images in computer graphics involves processing a massive amount of pixels. Data driven parallelism is used to divide the rendering task among multiple processors or GPU cores available, allowing for simultaneous rendering of different parts of the image. In genomic data analysis, analyzing large genomic data sets such as DNA sequence involves processing vast amount of genetic information. Data-driven parallelism can be used to divide the genomic data into chunks, allowing multiple processors to analyze different regions simultaneously. This accelerates tasks like alignment or genomic mapping. Now we will see parallel processing in sparse matrices. Generally, parallel algorithms are essential for improving computational performance by breaking down the larger tasks into smaller ones. These smaller tasks can be executed simultaneously across multiple processors or threads, significantly reducing the overall computational time compared to sequential execution, that is, executing each task one by one. Parallel computing is especially useful when working with large or complex datasets. By dividing the work and processing it in parallel, systems achieve better performance and ensure tasks are completed faster. Now we will see some techniques for parallel processing in sparse matrices. The first one is domain decomposition. Domain decomposition is a technique in parallel computing where a large computational dataset is split into smaller subdomains. These subdomains are then assigned to different processors, allowing the problem to be solved in parallel. This is especially useful in areas like scientific simulations, like climate modeling, for example, and matrix operations where computations can be performed independently across different sections of the data. How this works is, first, the entire domain is divided into multiple parts or subdomains. Each subdomain is handled by a different processor. These processors work in parallel to perform computations for their specific part of the domain. For many problems, some data from neighboring subdomains is needed. Thus, processors exchange information at the boundaries of their assigned domains to ensure accurate results. There are certain types of domain decomposition. One is geometric decomposition, functional decomposition. In geometric decomposition, the problem space is divided into spatial regions. In functional decomposition, different processors are assigned specific tasks related to different functions of computation. For example, one processor may handle matrix multiplication while another processor performs sorting operation. How this domain decomposition works in sparse matrix operations. We will divide the matrix into submatrices. Each processor focus on the relevant part with non-zero elements, ignoring the zero elements to save time. This approach reduces computation and speeds up matrix operations. The second one is graph based partitioning. The graph based partitioning is a fundamental technique in parallel computing where a problem is represented as a graph and it is divided into smaller parts, that is, subgraph. The goal is to distribute the workload effectively across multiple processors while minimizing the communication overhead between the processors. This approach is especially important for complex systems like social networks or matrix based operation where the dependencies between the data elements needs to be managed carefully. How this graph partitioning works is the problem is modeled as a graph. Nodes represent computational tasks or data points. Edges represent the relationship between these tasks. The graph is divided into smaller subgraphs, that is partitions, with each part assigned to a different processor or a computational unit. The goal is to minimize the number of edges between the different subgraphs to reduce the need for communication between the processors. Edges crossing between partitions require communication between processors, which can introduce latency, that is, the delay between the communication. There are different techniques for graph based partitioning, that is, edge cut partitioning, vertex cut partitioning, and multi level partitioning. How this graph partitioning is done in sparse matrix operations is the sparse matrix can be represented as graph, where rows or columns are treated as vertices and the non-zero elements create edges between those nodes. Using this graph partitioning, the matrix is divided into independent submatrices. Each processor works on a partition, and communication is limited to edges that cross partition. The advantages of this graph partitioning are load balancing. Each partition contains a equal number of tasks to avoid overloading for a single processor. Reduced communication overhead. By minimizing the cut edges, the amount of data exchange between the processor is reduced. So this improves the performance. Scalability. Graph-based partitioning supports large-scale parallelism, making it suitable for managing large data sets. And the last is GPU accelerated computing. In GPU accelerated computing, we'll use a GPU, that is graphics processing unit, instead of a CPU to perform computations faster. GPUs, originally designed for rendering graphics, have evolved into powerful tools for parallel processing, making them ideal for tasks that involve massive datasets and complex computations. How this GPU accelerated computing works is the CPU is optimized for general purpose tasks and sequential operations with a few powerful cores, but the GPU is designed for parallel workloads containing thousands of smaller energy efficient cores that process many tasks simultaneously. In GPU accelerated systems, the CPU handles the sequential parts of the workload and delegates the parallelizable tasks to the GPU. This approach allows complex tasks like machine learning, simulations, or data analytics to run faster by dividing the workloads between the both units. Why should we use this GPU accelerated computing? GPUs can run thousands of threads in parallel, making them ideal for computations involving large data sets like matrix operations, image processing, and neural networks. The throughput is also very high. GPU offer high computational throughput than CPUs, meaning that they can handle more operations per second for specific type of workloads. For certain tasks, GPU deliver high performance per watt, making them more efficient than relying on CPU resources alone. This results in less power consumption. Some applications of GPU accelerated computing are machine learning, image and video processing, finance, healthcare, and in some scientific simulations like weather forecasting. Thanks for watching.